Hello, we are group one, Kennedy, Jordan, David, and Alex. We're going to be going over chapter 3. So chapter 3.1, the basic physical laws of fluid mechanics. There's 3 methods to look into them. There's integral, which is large scale, differential, which is small scale, and experimental, which is just dimensional. And then we have analysis of control volume. So if you have a whole situation and you want to just look at one portion of it, you can do that through the control volume. And there's also some new things. We have volumetric flow rate, which is denoted as Q, and mass flow rate, which is m dot. And then the volume flow rate of a flow through a surface is this equation right here. And the n portion right there normalizes the velocity relative to the area. So the velocity must be perpendicular to the surface. And then Q, which again is the volumetric flow rate, it has this equation where n is positive outward. So the outflow is positive and the inflow would be negative. And then just relating volume and mass flow rates, we have m dot equals the density times the volume flow rate, and the volume flow rate equals velocity times the area.
Moving on to 3.2, which is the Reynolds transport theorem. This is used to convert a system analysis to a control volume analysis. This conversion formula changes based on whether the control volume is fixed, moving, or deformable. On the left, we have a picture of a fixed, in the middle is moving, and on the right side is deformable. Equation 1 represents a fixed control volume, which is in the first blue square. Equation 2 shows the transport theorem for a uniformly moving control volume. Equation 3, which is in the second blue square, shows the transport theorem for a deforming control volume. And in terms of the last equation, sometimes the flow crosses the boundaries of the control surface only at specific inlets and exits that are one-dimensional. Therefore, the flow properties are uniform. For a fixed control volume, the integral reduces to the sum of outlet and inlet terms.
And moving on to 3.3, which talks about the conservation of mass. The first equation under A on the left-hand side comes from the Reynolds transport theorem. And for steady flow mass conservation, it can then be simplified to the equation on the right, which states that mass flow in equals mass flow out, or if you want to simplify like the words even more, inflow equals outflow. And then for one-dimensional incompressible flow, volume flow in equals volume flow out, and that's just the flow rate form of the equation.
Moving on to 3.4, the linear momentum equations. There's 3 assumptions that are made. The fluid velocity relative to the original velocity is the same, therefore acceleration is 0. The sum of forces is a vector sum, and the force is acting on a system material, so therefore the system is a free body. These are vector equations, therefore they have 3 components, x, y, z. For a fixed control volume, it follows velocity relative to the original velocity, therefore there's not much change. For the one-dimensional inlets and outlet, this assumes it's a steady flow, so uniform pressure is independent of the shape and surface. The picture below demonstrates this. And for the final portion, the flux correction factor, this factors for the variations of velocity in a duct system, and is also a vector, therefore there's 3 components.
And that's it. Thank you.
Hello everybody, we're group 1 and we'll be discussing the given by the problem. Our rho is r, area is a, and velocity is v. But since it's a steady flow problem, all the velocities are the same. So I'll just be using a big V, and I'll substitute it when I'm simplifying the problems. Now for the free body diagram of this problem, I'll just retry it. For the free body diagram of this problem, we have inlets and outlets, obviously. So we have M in, v in. We have 3 going down, so I'll just write m dot 3 v3. And I'm gonna break 2 into 2 components because there's an x and a y based on theta. I won't be writing it for the problems right now, but I will be, I won't be writing in the free body diagram, but I will be writing in the problem. This is fy, fx, and a standard coordinate system, x, y. Okay, so just from what we learned, the summation of forces equals to the mass flow out, times the velocity out, minus the velocity in, times the velocity out. This is that big integral equation we had. So for the x component, and a quick side note, m dot is equal to rho VA, where rho in this case is R. So this is m dot 2 out 2, and since it's at an angle, we have to focus at the x component, minus m1, which is in, times velocity. So fx becomes rho, again R, times the velocity, which is the same throughout, so we're going to use v, times a, times the velocity again, cosine theta, minus same thing for the first portion. And this just simplifies to rho squared. Sorry, I'm factoring out currently. Rho RA, and I forgot the alpha. Rho times v squared times alpha a cosine theta. Actually, we can factor out the alpha. A alpha cosine theta minus 1. For y component, it's similar, but the difference is we're going to be focusing on the mv2 and m3 v3. So, and a side note, if the total area is equal to, sorry, the area for area 3 is equal to area minus alpha a, or I'm going to simplify to 1 minus alpha times a. Back to the problem, we have rho v squared alpha a sine this time minus rho v squared 1 minus alpha a for area. And we can just simplify this as rho density times velocity alpha a sine theta minus 1 minus alpha times a. There's more simplification, but this is fine for now. So for the second part of the problem, I'll be leaving as part B. It is given that the object is moving to the right at velocity b. So if we look at the object at any random point and we think of it in its perspective, we have a relative velocity of the object, which equals to vb plus the original velocity, because we're going towards it and it seems like it's moving faster. It's very similar to the first problem. The only difference is I'm going to substitute v for vb plus v. And I'm just going to skip some steps. This is equal to r vb plus v squared alpha a cosine theta minus r vb plus v squared a, which if you factor it out equals to this. Sorry. Times alpha cosine theta minus 1. VB, since there's no motion in the y direction, it really doesn't matter. the new velocities, because again, they're equal to 0. So we will be looking at like this. So this equals to, and this one will be a cosine. So alpha A sine theta times again, it's v squared because again, it doesn't matter that we're accelerating or we're moving in one direction. The change in velocity is not affected in the change of height. So R A times 1 minus alpha times v squared. Again, this simplifies to the top portion. R v squared alpha A sine theta. And that's it for this problem.